In a previous video, we looked at the syntax of lambdas and we saw that they offer a functional style of programming in contrast to the imperative style of programming that we've been following up to this point. In this video, we're going to look at one of the areas in which lambdas are used very widely, and that is in connection with streams. And streams are an alternative way of working with collections of data. We often create a stream from the contents of a collection, such as an array list or a linked list or a hash set. An array list or a linked list itself is not a stream, but those collections have a method called stream that will return a stream object that we can then apply various processing steps to in order to achieve a desired outcome. And it's during those processing steps that we're going to be making use of the lambda style of functional programming that we've been looking at. One of the interesting things about a stream is that we can actually create infinite streams, and that's an interesting issue to ponder. How do we ever finish a program if the stream is infinite? But streams themselves have features that allow us to say, okay, that's enough, I want to stop processing this stream now. Another feature of streams that makes them particularly significant is that we can often process the items in the stream in parallel, and that allows us to make effective use of parallel processing capabilities that the computer we're using might have. It's a lot harder to do tasks concurrently without using streams and their parallel features. Streams have a couple of significant features. The items within them are ordered, but we don't access the items in the stream with a traditional index as we might with something like an array list. Another feature of a stream is that it's immutable. We can't actually change the contents of a stream, but instead what we often do is we create a new stream using some or all of the contents of the original stream. So the processing of streams often involves what's called a pipeline, where we start with one stream, we apply an operation to create a new stream, and then we apply a further operation to create another stream until our sequence of operations achieves the task that we're aiming for. So there are three key operations that we typically perform on streams. Some or all of these will often be present in any of the stream operations that we perform. We can perform a filter on a stream. What that means is that we take our input stream and then we select some elements to be passed on to the output stream, but some elements do not pass on through. So typically the output stream from a filter operation has fewer items in it than the input stream. Another operation we often perform is what's called a map. The objects in the input stream are of one type, but the objects on the output stream are of a different type. Now, that doesn't necessarily always have to be the case. We can still perform a map where the objects in the output stream have the same type as those on the input stream, but we will have effected some form of transformation on the items on the input stream in order to make them suitable for the output stream. And then finally, the third sort of operation that we're going to look at is what's called reduce. And in this case, we want in effect to collapse the items coming in on the input stream down to a single element. So for instance, a typical example might be we have a stream of numbers and we want to sum those numbers. In effect, we would be performing a reduction from a sequence of numbers down to a single number in the output. So in the following slides, we're going to take a look at all of those operations, the filter, the map, the reduction, and we'll look at them in the context of the kind of processing that we might want to do with our National Park Animal Sightings project. And that will then allow us to provide the equivalent functionality that we saw in the previous video, done in a traditional style, but done in a functional style using streams and lambdas. Here's how we might illustrate the filter process. We have a stream of objects and we wish to apply a filter operation, that will mean that only some of the input stream will be selected to pass through to the output stream. So as noted previously, the output stream is typically shorter than the input stream. When we perform a map operation, then we're typically transforming the data coming in of one type to be data going out of a different type. So here, for instance, we've got some general objects and we're mapping each object to a corresponding numerical value. So when a map operation is performed, the output stream has exactly the same number of elements as the input stream. There's a one-to-one correspondence between the items in the input stream and the items in the output stream. And finally, the reduce operation collapses down all of the items on the input stream down to a single object or possibly a single value, such as a single string or a single numerical value like a sum. Now, the point about all these operations is that they are often performed in combination. It's not necessarily always the same sequence. We don't always do a filter followed by a map followed by a reduce. We could easily do a map followed by a filter, perhaps a second map, and then a reduction. So we can link these operations together in any sort of pipeline that we want in order to achieve the overall task. Here the idea is expressed at the bottom of the slide. We essentially want to find out how many sightings of elephants there have been. So the first step is to select from all the possible sightings only those that refer to elephants. So we want a filter operation to be performed where all of the sightings coming in the input stream, only those referring to elephants will appear on the output stream. And then, having selected only elephant sightings, the key item we're really interested in is what's the count number for that sighting. So now we perform a map from a sighting object on the input stream to an integer on the output stream. All of the other sighting information can be thrown away. It's only the count we're interested in. And then finally, once we have the individual counts of the elephant sightings, we can perform a reduction and sum those three values down to a single numerical value of 8. So expressed as a stream-based pipeline, we want to filter on the name of the elephant, we want to map the filtered data to the count, and then we want to reduce those counts to form a summation. How do lambdas fit into this? Well, each of those parameters to the filter, map, and reduce method calls will in effect be lambdas, or will have lambdas as part of their parameterization. So we will be passing a lambda into each of the filter, map, and reduce calls to say, this is the operation I would like you to perform on the data items on the input stream. So pipelines start with a source stream, and then there are potentially many intermediate operations, and then a terminal operation at the end that ends the pipeline. So those intermediate operations are going to produce a new stream for the next stage in the pipeline. And those terminal operations might have a void return type, so they might simply do something, but they can also have a non-void return type, so they can produce a result. And the reduce operation is a typical one that produces a result. What's the summation of the numbers if that happened to be what the reduce operation was? So let's look in a little bit more detail about what it means to write a filter operation, a map operation, and a reduce operation. The parameter to the filter call is always a lambda that produces a Boolean result. And Boolean result lambdas are called predicates. And the idea is that the lambda, when applied to an item in the stream, returns either true or false. If it returns true, then that item is to be carried over to the output stream. If it returns false, then the item is to be suppressed from the output stream and doesn't carry over. It plays no further part in the pipeline. There is no return keyword required for single statement lambdas, and what's typical is that predicate lambdas are single statement. The predicate can usually be expressed in a very concise way. Let's have a look at a few examples. Here we've got a predicate that returns true if the name of the animal in the citing object is elephant. So we invoke the getAnimal method on the citing object, and if the string comparator equals returns true when compared to elephant, then that citing object will be passed through to the next stage of the pipeline. So that's going to filter out all non-elephant citings from further processing. If we're only interested in citings which have a count greater than 0, then we might express the predicate as being get the count from the citing object, and if it's greater than 0, we want to allow that citing object through. In all other cases, we want to suppress that citing object. And then there are a couple of slightly curious looking predicates, but there are occasions when it's useful to either pass everything on through to the next stage of the pipeline or pass nothing on. So those last two predicates express that. At the bottom, we've got a simplified version of the overall task that we want to perform. So here we're not actually summing the counts, we're simply printing out the details of only those elephant citings. So we ask the array list to return a stream of all the citing objects. We then wish to filter those citing objects so that we're only selecting the elephants, and then we can apply a for each operation, a terminal operation, to the resulting stream, and the operation we want to perform is to simply print out the details of that citing. So here we print out details of only the elephant citings that are stored in the citings array list. So that's not the full task, but that's the first stage, which is to filter out the non-elephant citings. Let's look at the map method, the map operation, in a little bit more detail. So suppose we want to get hold of the details string for all of the citings within the collection. We are in essence mapping a citing object to a string object. So once again, we ask the array list to give us a stream of all the citing objects, and then we map from citing to the details string. So notice here that when we're returning something from a lambda, we don't need to use the word return. It's enough just to write the expression on the right hand side of the arrow symbol as the result of the lambda, and the compiler can work out that if we're writing a value returning expression there, then the implied return type here is string, and we don't need to express that via a return statement or a return type for the lambda. So we're mapping the citings to strings, and it's strings that are then being processed by the for each method. So each detail object coming in as a parameter is a string, and then we simply call the println method on that string. The reduce method is actually the most complex operation that we can perform, and it's complex because of the parameters that are required to it. It can be a little bit tricky to understand what all those elements are. So the reduce method takes two parameters. It takes what's called a starting value as the first parameter, and then it takes a lambda as the second parameter. And that lambda has two parameters. The first parameter to the lambda is what we call an accumulating value, and the second parameter to the lambda is one element of the stream. And the right hand side of the lambda says combine the element of the stream with the accumulating value, and then the resulting value from that will be passed on to the next application of the reduction to what remains of the stream. So let's try and look at that in a little bit more detail. So the lambda parameter determines how to merge an element with this idea of an accumulating value, and then that accumulating value becomes the next value for the next merge, and then the next and the next, and so on. And because there's no value to be merged with the first item in a stream, that start parameter stands in for what would have been an accumulating value preceding the first item in the stream. So let's put some flesh on that and see what we mean in practice. Suppose we have a stream of integer values, and those values are 4, 5 and 6, and we want to apply a summing reduction to that. In other words, we want to add up the numbers 4, 5 and 6. So we want to add the 5 to the 4, and then we want to add the 6 to the result of adding the 4 to the 5. So the question is, what do we do with the 4? What do we add that to? And that's why we have to provide that first parameter to the reduction, because that's the value that we want to add into the very first item in the stream. So one way of visualizing the reduction of the 4, 5, 6 stream is to say that we're going to call reduce on the stream of numbers. 0 is going to be our starting summation value, and then the operation we wish to perform as part of the reduction is to take our running sum, which is called ac, and the next element of the stream, which we call L, and then the body of the lambda combines those two values, the running sum and the value of the element. So when we start off, we're going to be calling reduce, passing a value of 0 as the first parameter, and the element that we wish to apply that reduction to is the 4. So 4 will be provided for parameter L, and the 0 will be provided for the ac parameter. And as a result of that, the body of the lambda will add 0 to 4, which means that then when we apply the same reduction to the remaining elements of the stream, 5, 6, now the starting value is 4, so that will be in the place of ac. The next element is 5, so we'll be adding 4 to 5 to give us the result of 9, and therefore as the final reduction is applied to the last element, we're providing 9 as the starting value, which is the accumulation of the 4 and 5 addition, and we're providing 6 as the element. We add those two together, so the overall result of that reduction is going to be 15. It can take a little while to see what's going on there, so spend a bit of time making sure that you understand the processes that are going through the systematic peeling off of the next item from the stream and applying the reduction to that and the running sum that's accumulating. Let's look at how we might make use of this in the context of the Animal Sightings project. At the bottom of the slide, we've got the traditional way that we would iterate over a collection using a for each loop and produce a sum of all the counts of all the sighting objects that are in that collection. So we have this running sum value called total that starts off at 0, and each time around the loop we're going to be adding potentially another count into that running sum until at the end of the for each loop that running sum will have accumulated the count for all of the items that we're interested in. So the for each loop iterates over the collection, picking each sighting up. It finds out if that sighting is one we're interested in. If it is, we go and retrieve the count, and then we add that count into the running sum, gradually increasing total. It's exactly the same process that's being applied in the top piece of code. So we're asking the sightings array list to produce a stream of its sighting objects. We then want to filter out so that we have remaining in the output stream only those sightings that are of interest, in other words, those that match the animal we're interested in. Then we're mapping those sighting objects to a count, and so the reduction is being applied to an input stream of numerical values, all those counts, but we know that they're the counts for the type of animal we're interested in. There won't be any other animals' counts in there. And then we apply exactly the reduction that we saw on the previous slide in order to create the accumulation. So starting with a running total of 0, we keep on increasing that running total by the next count, and then the next count, and then the next count, until the stream is exhausted, and then the result of the count that gets returned is what's the total sum of all the counts of the animals that we're interested in. So take some time just to appreciate and understand that that code is doing the kind of summation that we want, of summing only the counts of the animals we're interested in. There's quite a useful extra method that's been implemented in the ArrayList class that takes a lambda. So we've seen that we often want to prune the items in a collection. Now, when we ask a collection to return a stream, we don't actually make any modifications to the collection itself. Even if we do some filtering on the stream that's returned from the collection itself remains unchanged. But suppose that we want to remove from a collection all items in that collection that match some criterion. Well, the collection actually implements a method called removeIf, and the removeIf method takes a predicate, and we can express in that predicate the conditions under which we want an item to be removed from that collection. So here's the way in which we might remove from the array list of sightings all of those sighting objects whose count is 0. We call removeIf on sightings, and then the predicate that we pass in says if the count for this sighting object is equal to 0, so if that predicate returns true, then that sighting object will be removed from the collection. So we see two advantages here. We've avoided the typical incorrect usage of a for each loop with removal for a collection. We can't use a for each loop if we want to modify a collection, but we see a much simpler way to express the removal instead of using a while loop with an iterator, which would be the way that we would do this typically up to this point. So it's quite a nice, concise, expressive way of conditionally removing from a collection, making use of a predicate lambda. So let's look at how use has been made of these features in the animal monitoring project and see the stream and lambda based equivalents of the functionality that we saw in a previous video for this project. Here we see that the list can be easily printed. We can apply the for each method on the array list directly, and we pass a lambda in that says we want to call get details on the sighting and print it out. Here's how we might print sightings only of one particular type of animal. We perform a filter where only those sighting objects that relate to that animal are passed on through. And then for each of those sightings in the output stream, we then again want to call the getDetails method and print out its results. Here's an example where we use both filter and map. So we want to print the sightings by an individual spotter. So once again, we provide a predicate to filter out all those sightings that are not by this spotter. And then we map the whole sighting object to a string, the detail string, because that's all we're interested in printing, and then we print all of those out. And then finally, here's one to return the count for a particular animal that uses all of those features that we looked at on the slides. So we filter on the type of animal, we map the sightings to the counts, and then we perform a reduction on all of those counts to return the summation of the counts for that animal. So the functionality in this version of the class is entirely equivalent to the functionality in the previous version of the class that used the more traditional while loops and iterators. To summarize, streams and lambdas are an important and powerful new feature of Java, and they're likely to increase in importance over the coming years. So collection processing is increasingly going to be moving that way. You'll see more and more code written to process collections using lambdas. Another area where lambdas are very common is in the use of building GUIs for event handlers, for instance. We can always convert a collection into a stream for processing in the form of the kind of pipelines that we've seen. And typical pipeline operations are things like filters, maps, and reductions. And a particular benefit of streams is they make parallel processing much easier and therefore potentially allow us to take advantage of the concurrent hardware that we might have on the computer that we're using.